Hey everyone. So this chapter in chapter 24 is about a new concept, right, called electric potential. You may have heard of it referred to as another name, voltage, but that's the same thing. Electric potential and voltage, they are interchangeable. It is related to the electric field and the electric force, and it's also related to potential energy of a charge. But let's see exactly what it is, right? What differentiates it from those, and what it really means for a charge. Okay? So, to start, if a charge is in an electric field, right, I can denote that by this, right? The electric field goes from left to right, in this case, right? If we put a test charge in this field, well, let's say we put it right there, test charge of magnitude q. If we put it nearer, more near, the positive side, it will be repulsed and want to be accelerated to the right, right? So it'll travel in that direction, okay? And so if it goes from, say, I don't know, um, the left to the right, that distance, if we call that distance s, then that's its displacement vector. Okay, we'll call that ds, right? The differential displacement vector, and we'll see why it's ds very shortly. Okay, if this particle that's in this electric field is accelerated, it feels a force, right? From the Coulomb force, K Q Q over r squared, sometimes written like this, QE, right? And I guess if you wanted to make it a vector, it's in the generalized r hat direction, right? And so you could set this equal to ma and find some acceleration, yes, but we're not necessarily worried about the acceleration per se. Okay, we're worried about the meaning of its movement in this field. Okay, so if there's a force on it, that means that that electric force is doing some amount of work on this particle. And if you remember back to chapter 7, I know that was a long time ago, it's integral of some force dotted with some displacement, right? And because it's an integral in this form, it's some differential displacement. In the case that I've drawn, that displacement is s. And this chapter uses s for path, right? The path length. So I'll stick with s instead of dr or dx like in the past. Okay, but this is work, right? And so the electric field would do, well, this amount of work on a test charge, okay, of magnitude q. You may also recall from chapter 8 that work is equal to negative the change in potential energy, right? Potential energy U. If we think back, we can perhaps see where that negative comes from, right? Let's do a quick example from gravity. Say we tossed a ball or picked up a ball off of the ground. So this was, there we go. Height 0, and it picks it up all the way to a height h. So, whoops. So at height h, it will have, let's go, potential energy of mgh, right? And so as this ball is moved upwards, right, its displacement is upwards, in this case, well, y, the vertical distance. And so it moves up a certain height h, but all the while there's a gravitational force downwards. Right, so we can say displacement, let's use y, okay? So the work done by gravity, because it's in the opposite direction, and the fact that we have a cosine here, right, that means that it'll do negative work. Right, so the negative work comes from the fact that gravity is downwards, other direction as its displacement. And the change in potential energy, final minus initial, since the ball is moving up, is equal to positive. All right, let's do this here. The work was minus, let's do this, mg H. And that's equal to, well, mgh minus 0. I'll leave that as plus delta U. And so just move the minus sign into the other side, and we can see that work is equal to negative change in potential energy. Right? This was for a object on the surface of Earth with the force of gravity. That's where the negative comes from. And if you move the ball down, so starting at a height up here and going down to a height of 0, well, in that case, it's slightly different. Right? In this case, the displacement is down. And so now the work is in the same direction. So we have positive force times the distance of h. And that's equal to now final minus initial, that's equal to a negative delta U. So in this case, work is equal to, again, negative delta U, right? Yes, they're the same, mgh, and that's the point. But the negative is always there, even still. So let's translate that example now to the physics 4B electrostatics realm and see how that applies to test charges in the electric field. Okay, my magic eraser here. Okay, now instead of the force of gravity, we have the electric force, QE. So let's put in that to our integral, keeping the vectors for now, ds, and I allege that that's equal to negative delta U. Okay, that U isn't necessarily mgh, right? It's just some change in potential energy. For right now, I'm going to keep it as a capital U. And I'm going to rearrange this a little bit. I'm going to bring the Q to the right side and the negative to the left, turning the expression into the following. And so now, it may look a little weird. We have a negative integral of some dot product, some differential dot product, and that this equation tells us that that's equal to the ratio of the change in potential energy per charge. So let's take a look at what this means, okay? That test charge again, right here, that test charge, if it starts on the left side or closer to the net positive side and travels to the right, which is the net negative side, that's what it would naturally want to do, right? If released from rest, it would naturally want to be accelerated to the right. Okay, so let's take a look at the change in U here. Well, on the left side, it has a greater potential. Sorry, that's a bad word. I don't want to necessarily use that word. It has the greater tendency to be accelerated on the left side here than on the right. Okay, so tendency or a greater ability to be accelerated, right, across a distance s. If it's on the left side here, it'll be moving faster after having traveled the distance s than if it started over here and traversed the same distance s but over in this direction, right? Because when it starts here, it's further away. So there's a weaker electric force than over here. So the closer a particle is to the net positive side, the stronger the electric force, right here. Thus, the stronger or the larger the initial potential energy. Okay? And so if it moves from left to right, what I'm saying then is that it should decrease in potential energy. Right? It should decrease in potential energy. And so that says this negative sign here tells us that. Okay? As a particle goes from the left side to the right side in the same direction as the electric field, so E and ds are in the same direction, therefore the angle in between them is 0, this left side turns into a net negative ES or whatever it is, right? A negative something. So that means that the change in potential energy is decreasing, right? It's more negative, it's getting less. And that's exactly what's happening as the charge moves further away from the net positive side. Okay? Flip that around. Now let's take a look at the ds when the charge starts on the right side and travels leftward. Okay? Now if the particle starts at a position over here, right? So kind of think of this as it has a lower potential energy, right? It has a lower tendency to be accelerated. It doesn't naturally want to go towards the positive side, right? It naturally wants to keep going this way. So thus you need to add energy to that particle in order to push it to the left or push it back towards the positive side. So in that case, the electric field and ds are in opposite directions. Thus, the angle in between them is 180. And now, cosine of 180 is -1. That cancels out that negative, and this side becomes a net positive, ES or whatever. So when you go from the right side to the left, the delta U is positive, which means that you're increasing potential energy. Right? You're increasing potential energy. That's the exact analog to when you raise the ball upwards in the air. It's going against gravity, and you're raising its gravitational potential energy. In this case, you're kind of increasing its electric potential energy. Right? So this minus sign here, right there, that's essential, right? That's part of this. And I haven't said it yet, but this is what the potential is. And we write that as V. Electric potential, also known as voltage, right? Those two terms are interchangeable. Electric potential and voltage, same thing. So that's why we give the variable for the potential capital V after a voltage, right? It's measured in units of volts. And so a voltage is a particle's, potential energy, right? It's the ratio of the change in potential energy per particle, okay? And so it's kind of a way to standardize the tendency for charges to be accelerated. We don't have a direct analog in the gravitational sense, because the gravitational force, at least on Earth's surface, is pretty much always constant. In this case, the force doing the accelerating or doing the work doesn't have to be constant. We can change the magnitude of this electric field, right? Thus, we change the amount of delta U, okay? So, not quite the same. But hopefully this gives you a sense of where or what the voltage is. It's a tendency for a particle to be accelerated in an electric field, and hopefully shows you that this minus sign is essential. Okay, so in summary, real quick, if E and displacement, I'll write that as ds, are in the same direction, or let's do this, are parallel, right? Boop, boop. Then the delta U is negative. Let's write it like this. Delta U is negative, right? If E and ds are antiparallel, delta V is positive. Okay? Delta V is positive, meaning you are increasing the electric potential energy. And in the above case, if delta V is negative, you're decreasing the potential energy. Okay? All right, thanks for watching.